I'm presenting my research on the fracture of brittle materials under uniaxial compression. I know it's a fracture mechanics conference, and everyone is an expert in some field of fracture mechanics, but compression stress fields are completely ignored because they're not very straightforward as tension stress fields. So my research is quite basic, talking about the principles of fracture mechanics when we think about them in compression stress field. So here's an outline of my presentation. So for introduction, if we look at this graph, it's for the total energy in, let's say, two molecules or two atoms. So it's the intermolecular, interatomic forces and the energy on the micro level. So if you look at the left-hand side graph, it's the energy. So this is the radius between two atoms or two molecules, which is of the lowest energy. So this is the normal phase for any material. If we try to pull or separate the two atoms far from each other, this energy is increasing a bit, or if you look at the force, it's decreasing. So if you are trying to pull them, you don't need too much force. If you try to pull them, you don't need too much force. But if you try to push them, to compress them, the force keeps going high and high until infinity. So if you have two atoms and you try to press them to touch, it's impossible. So for any interatomic bond, if you want to crack this bond, by pressing it, it's impossible. You need to pull it to crack it. And to elaborate on this, let's look at this cube of solid concrete. So if you have this solid concrete, no air voids, nothing in it, just pure concrete solid, and you put it deep in the ocean, very, very far deep, 2 kilometers, 6 kilometers. So you have tremendous pressure, but there's no cracks happening for this one because it's solid, it's completely solid. So you won't be able to crack it because pushing on any interatomic bond cannot break the bond. You have to pull it to break it. So let's apply this on compression stress field. So if you are pressing on anything, it's impossible to crack it unless you have something that causes tension in this material. So according to Griffith, the very basic principle we all know, when you look at the glass samples with thick diameters, it has some strength, and then when he made the samples thinner and thinner, he got higher strength because of so many factors. One of the factors is eliminating all the flaws in the material, or most of them. So all materials have flaws, and it's widely believed that these flaws are the main cause of initiation of any cracks. So we have different types of flaws, some regular, some irregular, depending on the material you're studying. It could be some discontinuity, it could be an air bubble, depending on the material again. So I'm studying concrete or any similar material, so one of the main flaws in concrete is circular flaws due to the presence of some air bubbles. So that's what I'm studying. So again, to compare compression to tension, if you are pulling a piece of brittle material, you'll get this kind of crack. And you can study all the parameters for this crack. If you want to do it linear, non-linear, plastic, extensive, advanced modeling, you can do this for a crack under tension. But if you have the same solid part of the same material and you're pressing on it, you're going to get some kind of cracks like this, parallel to the applied stress field. And unfortunately, you can't do so many studies on this. So I have a paper published in Theoretical and Applied Fracture Mechanics covering all the review of the previous studies for compression. And unfortunately, there is no theorem that you can apply directly to compression stress field. So many people modeled stuff, but all the numerical modeling done for this type of problem is one case modeling. So they are modeling what they got in the experiment, either by imaging or CT scans. So they are modeling what they get and trying to justify it, but not having a theorem to be applied generally, which will have intention extensively. So let's look at this equation for K1. You have, this is the basic equation, so you have K1 is some factor sigma root pi A. So in tension, if you have this infinitely thin crack and you're applying tension, as long as the crack is growing, you're having K growing and growing, and it will keep growing until failure, until it reaches the K1C and it fails. And there is no possibility, there is no other possibility but having K growing with crack length, because this is the governing equation. But if we have an infinitely thin crack in a compression stress field, infinitely hairline thin crack in a compression stress field, it doesn't do anything. Why? Because it doesn't change the strain energy within the specimen or within the model, so nothing has changed. And this infinitely thin crack doesn't affect anything. But let's keep in mind that in tension, K1 keeps growing infinitely with the A growing. So what we did is we modeled this model, which has an air bubble, but exaggerated in size. So we have a 20 millimeter or other values of this hole in this model. It's a 2D model. We have the mesh size around the model 0.01 millimeter, and we modeled the crack in increments of 0.05. This model was built on Frank 2D. It's a basic old 2D modeling software. The interesting thing about Frank is it's very simple and it has all the crack propagation remeshing built in, so I don't need to use so many other softwares developed. So just this software I used to study this problem. So this is how it looks like, the mesh around the discontinuity we have. So we did 5 models on Frank. 3 of them had circular voids, 10 millimeter, 20 millimeter, and 5 millimeter, to study the effect of the size if it is circular void. And then we have 2 elliptical voids. One of them is 10 in width by 20 height, and then one is 10 width by 5 height, to see the effect of flattening this circle, so to make it a vertical ellipse or flattening it. So you can compare the effect of the height, comparing the 2 ellipses and the 10 millimeter hole, and you can compare the effect of width, comparing the 5 millimeter and the 10 millimeter width, so they both have the same height and then different width. And we modeled the C10 and C20, the 10 millimeter, the 20 millimeter on Abacus, to get the estimation of the total strain energy within the model and the interaction. It's easier in Abacus because strain energy is not very user friendly, it's too old for any of you who used it. So this is what we got in terms of K1, and I'm using K1 because having these types of discontinuities results in tension on the higher end of and the lower end of the discontinuities. So we have tension in here and here, equivalent to the end stress, according to the geometry of the shape. And then we have compression on the side, 3 times in case of circular, 5 times in case of the flat ellipse, and 2 times in case of the vertical ellipse. For those who studied these geometries, you all know these values. So we got K1 against crack length For C5, C10, and C20, the circular ellipses. And then this is the vertical ellipse, 10 width by 20 height. And then this is the flat ellipse, 10 width and 5 millimeter height. If you look at this plot, the interesting thing about all the plots for indiscontinuity in compression stress fields is the K value keeps going higher and higher until a certain value of crack length, and then it gets low, which is completely opposing what we know in tension. So in tension, as the crack grows bigger, K keeps going up and up. But in compression, as crack grows bigger, K keeps going up until a certain point, and then it goes down. This is at a certain load. So this is all for an applied 1.3 millimeter displacement. But if you increase the load, then you get a different plot, but shifted and bigger. So then, if we look at these plots, what we understand is, okay, you press on something, you get a crack length, a certain crack length, and then it can grow bigger because K just dissolves, just gets low. If you want this crack to propagate more, you have to apply more load. There's no unstable crack propagation in compression. Opposing tension, you have unstable crack propagation. In here, there's no unstable crack propagation. These are the values for the plots I showed you. So the peak K1 values depending on the shape. So when you have bigger sizes of circles, the K1, the peak K1 is higher. If you look at the ellipse, the flatter ellipse has way higher K1 compared to the vertical ellipse. So the horizontal ellipse has way higher K1 compared to the vertical ellipse, which is opposing anything you think eventually. So when you look at the plots and the shape of the voids I used, you'll think, okay, the vertical ellipse is more critical, but numerically the horizontal ellipse was bigger, was more critical. And then the crack length, which has the peak K1, so crack length grows bigger for the growing circular voids, and then for the flat ellipse, you have 1 millimeter crack length at the peak K1, and then for the vertical ellipse, it's smaller. And then we modeled C10 and C20, the 10 millimeter and the 20 millimeter holes in abacus to get the estimate of the total strain energy within the specimens, within the samples. So the total strain energy with no cracks, just the presence of the voids, we have the reduction in strain energy for a model without any voids, and then a model with the void we're using. So this void reduced the strain energy, total strain energy in the model by 0.12%, and then the 20 millimeter hole reduced the strain energy by 0.471%. So if you look at these numbers, if you divide this by this, it's 4, which is the volume to the volume. So the reduction in strain energy is directly proportional with the volume of the circular void. And then if we look back at the K1 for C20 and K1 for C10 and divide them together, the factor is 1.414, which is the square root of 2. So doubling the size of the circular void resulted in square root 2 factor of the Q1. The total strain energy decreased by 0.06% for C10 and 0.02 for C20 for a 6 millimeter crack. So if you have a 6 millimeter crack, you have a 6 millimeter crack in a model that big, 400 millimeter by 500 millimeter, the reduction of strain energy is only 0.006%. So this can emphasize and elaborate what you have if you're having a concrete cylinder test. If you have a concrete cylinder test, you have so many hairline cracks, and the load, you can see the load is constant, and then it drops. So you can have as many hairline cracks as you want, and they don't affect the energy that much, they don't reduce the end reaction that much. So the end reaction only decreased by the same value, 0.006% in case of having a 10 millimeter bubble, 10 millimeter hole. So it's not changing much. It's not changing much. So to conclude what I have, bigger voids generate longer cracks. When comparing heights, the flatter void is more critical. When comparing width, the wider void is more critical, definitely. And then the reduction of strain energy is direct proportional to the volume of the void, and it's very, very small. So you can't compare them and get values that can be used in extensive studies. That's all I have for you. Thank you for your attention.